So we started discussion on the support vector machines, which are also called as kernel machines, for a very specific reason because they use the kernel engineering for handling the non-linear classification boundaries. How it happens that we are going to see. Why they are called as support vector machines? That also we are going to see. So what is the concept of support vector? We just discussed last time, but I could not elaborate more because of the lack of the time. So I'm going to elaborate it today, that how it basically happens. So very quickly, basically it is a supervised machine learning technique. That means the data is labeled, targets are given, and as we have discussed last time, support vector machines can be used for classification purpose as well as regression purpose. But mostly you will see that SVM is used for classification purpose because there are other algorithms which do better than SVM as far as the regression is concerned. So mostly SVM is used for classification. So it's more powerful way to deal with the complex nonlinear functions that we are going to see. And the basic reason for this, if anybody asks you the question, like how they handle the nonlinear boundaries, your answer should be they use kernel engineering. Okay, they use kernel functions. Okay, so this concept we are going to understand in details today. So uses kernel approach for complex classification problems, popularly called as kernel machines, and that's the reason they are called as kernel machines. So SVM, another name we can say it's a kernel machine. SVM are also called as large margin classifiers for a very specific reason. Last time we discussed, it is like no man's land. Okay, this is to ensure that there should not be misclassification, and that's why when we draw the classification boundary, actually SVM introduces the margin. Okay, margin is like a buffer zone. Okay, it is no man's land. Okay, but this is just to explain the concept. Actually, it is technically called as margin. Okay, so there is a margin from the classification boundary, and that margin is typically, we are going to see later, it is -1 and 1. So to left hand side, if it is -1, to right hand side it is 1. So total distance between two margins is actually about 2. Okay, so that we are going to understand later. So try to understand, support vector machines are basically called as kernel machines. The reason is they use kernel engineering. Okay, kernel functions. This is also called as feature engineering. Okay, we are going to talk about it. They are also called as large margin classifiers. The reason is because the margin is introduced about the classification boundary to avoid the misclassification. Okay, to avoid the misclassification. How? That we are going to see. So in this kernel machines, already we have seen that this is typically a discriminant function based. Okay, so initially in classifiers, we talked about different approaches for the classification. One is discriminant function. Okay, sorry, discriminants like linear discriminant analysis. Second one is discrimination based, that is discriminant functions, and the best example of discriminant functions is kernel machines. And the last one is generative approach. So base classifier we have already studied as a generative approach, where we have actually calculated the probabilities, posterior probabilities. Here we are modeling the probabilities. Here we are not actually calculating the probabilities. Probability is modeled, and how it is modeled, it is based on the classification boundary. So it is simulated. I mean, uh, rather than using the word simulated, the best word is modeled. Okay. So class probability, when y is equal to 1 and y is equal to 0, so it's binary classification, and these probabilities are modeled with the help of classification boundaries. So it is discriminant based function. So we need not estimate the densities, we need not estimate the probabilities. How the discriminants are defined, and the discriminants are defined in the form of support vectors. So we are going to understand the concept of support vector here. Already we have talked about the use of kernel functions. So application specific measures of similarity. So later we are going to talk about, basically we are going to see how kernel engineering is used. There we are going to see how the exponential basis, that is Gaussian basis, it is used for kernel engineering. So that we are going to do it. So no need to represent the instances as the vectors. Okay, so there is no specific requirement as such to basically represent every sample as a vector. Convex optimization problems with a unique solution. So this is a requirement of any optimization technique. Basically, be it a regression program or classification program, we have seen that there is a specific error function. In classification, at the start, we have seen that the error function which we have used in the regression as it is cannot be used in the classification. So we modified that function, and it is written in the form of log likelihood. Okay, y into log of y cap plus 1 minus y into log of 1 minus y cap. So that is the form. And why we brought this form? To make the error function actually convex. Okay, so that exercise we have already done in the beginning of this unit. So this is typically a convex optimization problem. Why it is called as convex optimization problem? Because the shape of the error function is convex, and this has got a unique solution. This is very important. One global minima, one unique solution. So what is the concept? Let me elaborate the concept here. So suppose we have this samples as one class. Let's say y is equal to 1. So this is a target. This is a target class. So all these plus samples are belongs to y is equal to 1 classifier. And let's say all these red samples are belonging to y is equal to 0 classifier. That means whenever the data is given to you, data will consist of all the samples with target values. Okay, so like these are some sample values x, and this is y. So say these are all these red points are y is equal to 0. These are the target points. Similarly, you will have for y is equal to 1. So this is how the labeled data is given. Okay. So here you may have the blue samples also, some x values and corresponding y is equal to 1. So this is the target class. And for this, we need to fit a function, okay, that is classification boundary, such that it will introduce a margin. Okay, it will introduce the margin. What kind of margin? This should introduce the margin which is maximum margin. Now what is the meaning of maximizing margin? Let us try to understand. Suppose my classification boundary, it is like this. Let me draw it. Okay, so I'm drawing the boundary. Suppose the boundary is like this. I'm sorry. Okay, so assume that this is a straight line. So this is the classification boundary. So what will happen in this classification boundary? Look at this. This sample is very close to this classification boundary, whereas this sample is away from the classification boundary. So you can see that as far as the margin is concerned, margin is the distance of closest samples. Let me tell you. Okay, margin, what do you mean by margin? It is the distance of closest sample, closest sample point from the